Okay, now we look into 12.3 where the line integral is actually, the concept of line integral is actually work done by the force. So the work done by the force is represented by the terminology of, sorry, W here, across a curve C where the force need to be applied with respect to T to move from one point to another point. So the same concept that already explained just now, where F we represent in terms of the function RT, where the curve R is always changed with time, and we dot product with the dr over dt. That, what does it mean by that is actually is a work done by the force F in a line integral of the scalar component F dot t over the smooth curve from point A, initial point, to terminal point, point B, as shown in this figure. And the sign of the number we calculate with this integral depends on the direction in which the curve is transverse. As I mentioned, when we dealing with the line integral, we are dealing with magnitude and also the direction. So the direction is important when performing the line integral, or when we calculating the work done for this case. Alright, let's look at this example of 12.5. Find the work done by the force field. Just now previously we look at the example already. Now the force field F, vector F, which is y minus x squared in the I direction, plus z minus y squared in the j direction, and x minus z squared in k direction along the curve RT, where ti plus t squared j plus t power of 3 k, where the t is from 0 to 1. And this is how the curve looks like, and the force being applied to move the point from 0, 0 to 1, 1, 1. Alright, now we transform RT is actually t squared in the y component and t power of 3 in the z component. So y minus now we transform F RT. So y is actually t power of 2 minus x squared t power of 2. So you get 0 here. And then z minus y squared t power of 3 minus t to power of 2 power of 2. T power of 3 minus t power of 4. And x minus z squared t minus t power of 6 k. That is FRT. Now we compute R prime t. And R prime t, as mentioned, t power of 2 and t power of 3. When you differentiate it, you will get 1, 2t, and then 3t squared here. And then you do dot product. Okay, dot product, the one that you get from here. This is F R T. We dot product with R prime t. Okay. And then you will get, when you do dot product, you will get the scalar function. This one is scalar. You will get this answer. Alright, and then you integrate it from 0 to 1. How do you know it's from 0 to 1? Looking at the curve here, it can only take the value from 0 to 1, 1, 1. Okay. And then you integrate from 0 to 1, you will get 2t power of 5 over 5, 2t power of 6 over 6, 3t power of 4 over 4, minus 3t power of 9 over 9, from interval from 0 to 1. So when you replace the value, you will get the answer is 29 over 60. And let's look at another example of 12.6 when you need to find the work done by the force field X, Y, and Z along the curve parameterized by RT is equivalent to cos pi t, and then t power of 2, and then sine pi t. Alright, FR X, Y, and Z. X is cos pi t here, t squared here, and then this one sine t. And then we integrate the the RT. This is R prime T. Sorry, integrate pula. Differentiate RT, you get R prime T, and you will get differentiation, of course, you will get sine, and then differentiate the pi t, you get negative pi here. And then t power of 2, you get 2tj, and then here you will get positive cos pi t, and then you differentiate the inside part here. And then you do dot product just now, and you will get a scalar where this one can be negative and positive will be 0, and you leave it with 2t power of 3. And now the t is moving from 0 to 1. You find the integration of that, then you get the work, or the work done in that particular curve, which is equivalent to 1 over 2. Alright, let's look at the concept of path dependence. So the line integral generally depend on not only on the f, but also the end point and the terminal, initial point and terminal point, the end point of A and B of the path. For instance, that we have the curve like this. Both curve are ending and starting at the same point, A to B. For the curve C1 and the curve C2. Two different curve, but starting and ending point at the same part. So for curve C1, this is actually the function is R in terms of RT, T, T, and 0. But this one is T power of 2 and then 0 for the second one. So this one is actually R to T equivalent to T power of 2, 0. But here is R1 T is T 0. Okay, right. So if you find the R1 prime T also, you will get 1, 1, 0. Here you will get 1, 2, T, 0. Two different R prime here. Okay, and if you do dot product, you will get also the same, the different thing. One is T power of 2, and then another one is 2T power of 2. And if you take the integration of 0 to 1, T to the power of 2 dt, you will get 1 over 3 here. But here, if you take the integration of the same interval, 2T power of 4, you will get 2 over 5. That give different value respectively, although that is start and end at the same point. So as an additional information, if a vector function is the gradient of a scalar function, this vector function is known as conservative vector field, and its line integral is interestingly independent on the path. However, if C1 and C2 produce the same, I mean if you do that, the C1 and C2 will produce the same value if you have the conservative vector field. But there are cases that you have two curve that start and end at the same point, but then again will give the line integral or work done differently. Okay, alright, let's look at the this example. Evaluating the line integral with vector function f x y, x minus y, and then xj. The curve C is a closed curve, that form a unit circle. A closed circular curve can be parameterized as below, where the RT is given by cos Ti and then sin Tj. And we know that interval is because it's closed curve and perform a unit circle, so you know that the angle is from 0 to 2 pi, and also the radius is 1 actually. Alright, now we transform the FRT first. I like to do this step by step like that. So we have x and negative y. X is cos t, negative minus sin t, and then x cos t. Alright, the dr RT is given as this. You differentiate the cos, you get negative sine, and then you differentiate the sine, you get cos. So you do dot product. Okay, you do dot product, you will get cos t minus sin t multiply with sin t plus cos power of 2t. So in other words is cos negative cos t sin t plus sin power of 2t plus cos power of 2t. So sin power of 2t plus cos power of 2t, this one is 1. So it's equivalent to negative cos t sin t plus 1. That's why you get this. Okay. So here you get sin t cos t. Integrate it, you will get cos t over 2 because you can use substitution. You integrate either one. U can be cos t, du will be sin t dt. So it's easy lah. So you will get this answer, and you integrate it with the interval 0 to 2 pi, you will get the answer is equivalent to 2 pi. Alright, 12.8. So evaluate the closed curve line integral given as this, where C is the square cut from the first quadrant by the line x equivalent to 1 and y equivalent to 1 counterclockwise. So the curve looks something like this. Counterclockwise. Okay, C1 go to C2, C3 and C4, you go back to the origin 0, 0. So there are 4 lines that we need to integrate here. First is C1, C2, C3 and C4. Alright. So the first integration is actually C1 negative y squared dx plus xy dy from the equation here. And from here, from the first line, x is equivalent to t, but y is equivalent to 0 because it's on the x-axis. So x equivalent to t, from here x equivalent to t, dx will be equivalent to 1. Okay, so dx is equivalent to dt. Here, that's why dx is equivalent to dt. dy over dt cos 0 lah. So you transform it here. C1 from 0 to 1. Negative y squared. Negative y squared, y equivalent to 0. 0 power of 2. And then dx. dx is equivalent to dt. And then plus xy. X is t. Y is 0. And then dy. dy is also 0. dt. This is what you need to do. So this one you get 0. And then here you get 0 because you need to integrate 0. That's how you get 0 here. Okay. For the second curve, for the second curve now, x is equivalent to 1, because at this line, x equivalent to 1 and y from 0 to 1. So x equivalent to 1, dx will be equivalent to dt, y equivalent to t. And when you differentiate, you get 1. So here you transfer C2 negative y2 dx plus xy dy. You transfer that negative y2, which is y equivalent to t, right? Negative y power of 2, negative t power of 2. And then dx. dx is 0. This is dx. And then xy. X is 1. This is x. Y is t. Multiply with dx. dx is 0. So you will leave it with this one only. So when you integrate, you will get this answer. Okay. This one is 1. Sorry. dy. dy. Sorry. dx equivalent to dt. For this one. This one dy. So if it's 1 lah, dy is 1. Okay. So you will get this one 0. You will get this component only you need to integrate. You will get it as 1 over 2. Right. And then for the third curve, y equivalent to 1 now. Your x equivalent to t. So your dx will be equivalent to dt. And then dy equivalent to 0. And you replace now C3 negative y squared dx plus xy dy. You replace it here, you will get equivalent to 1. Same goes to C4. C4 is actually x equivalent to 0 and y equivalent to t, but now the interval is from 1 to 0. Okay, so when you solve it, actually you don't need to worry so much on the interval, because you will get this one 0 and this one also 0. So when you add it together, the first one you get 0, half, and 1, so you get 3 over 2 as the answer. Okay, last example, 12.9. Compute the closed loop line integral over the counterclockwise rectangle of 1, 1, 3, 1, 3, 2, and 1, 2. So how does it look like? Okay, let's say that this is x and this is y. Okay, so this is 1, 2, and 3. This is 1 and 2. Okay, so it goes like this. Okay, now this is how it look like. So this is your C1, C2, C3, and C4. Same goes lah. But now the only difference is your C1 now has xy dx plus xy dy. And x is equivalent to t, y equivalent to 1. So this one will be 0, dy will be 0, dx will be equivalent to dt. So xy dx is 1, and then you replace it here, you get 0 here. So you integrate this part, you will get this answer. Then for the second curve, C2 xy dx plus xy dy. X is equivalent to this one, C2. X is equivalent to 3. So you get x equivalent to 3 and y equivalent to t. Dx over dt will be 0. Dx will be 0 then. Dy will be equivalent to dt. So here 0. X is 3, y is t, multiply with 0, and then xy 3 multiply with t, dy is equivalent to 1. Okay, you get, and then when you replace the value, you get 9 over 2. Same goes with the C3 now. Now your C3 is this one. Y equivalent to 2, x is equivalent to t, because x is always changes along this line. So here is dx equivalent to dt, and then dy is equivalent to 0. So you replace it here, you will get this component is 0, and here is 2t. Integrate from 1 to 3, so you get negative 16 over 2. C4, from here to here, x equivalent to 1, and then y is t, equivalent to t, and we need to integrate from 2 to 1, because now it's going down. And then you will get negative 3 over 2. So you add it together, you will get the final answer equivalent to negative 1. So the solution of line integral involving a closed curve can be tedious, and when the closed curve is defined by multiple section as shown in 12.8 and also 12.9 here. In some cases, it will be more convenient to relate a closed curve line integral with the integral involving the curl of the vector function over a surface that is bounded by the closed curve. So we will look into that in the form of Green's theorem, and also will elaborate further week 14 when you learn Stokes' theorem. Okay, all right, thank you.